All right. Okay, everybody. Thank you very much. I want to talk about BoLD, which is the next generation challenge protocol for Arbitrum. And I'm going to start with the big picture and situate what role a challenge protocol plays in an optimistic rollup. This is a pretty typical rollup architecture that describes how Arbitrum works today. You see at the upper left, the sequencer. This is a component which takes in arriving transactions and publishes a canonical list of which transactions have arrived at the chain and in which order. Over on the right is the state transition function, which specifies the semantics of the chain. So if you are a node or an observer of the chain, you can take the transactions from the canonical sequence and run them through the state transition function one at a time. The state transition function takes the state of the chain and one transaction, and it updates the state and produces an L2 block. And then finally, down here on the lower right, we have the settle to L1. This is the all-important fraud-proof component, which is settling the results. So because the state transition function is deterministic and the transaction sequence is canonical, everyone can compute for themselves what the state of the chain is and what the history of the chain is. So the purpose of the settlement protocol is to tell the L1 Ethereum chain what the state is, so that you can do bridging either to and from Ethereum or bridging to somewhere else. So what we're talking about right here in this talk is the settlement protocol. Okay, so here's how it works currently in the Arbitrum stack. Each one of these boxes represents what's called an assertion. And so an assertion is making a claim that at some L2 block height, there exists a block, and the hash of that block is something. And as well, each of these assertions has a pointer to a predecessor assertion, which must be earlier in the claimed history. And you see here the protocol in operation. The assertion on the upper left is green and it's marked confirmed. That means that it's been accepted as part of the canonical history of the chain. So there is a single chain of these green blocks going all the way back to Genesis. Down here, we see an assertion that's been rejected. That means what you think it means. And the ones up here on the upper right are pending, which means that the protocol has not yet decided whether they will be confirmed or rejected. And as you can see, there's a fork in those pending assertions. So you might ask, why do we have assertions rather than just asserting blocks? And the answer is there might be 10,000 blocks of height difference between one assertion and its predecessor. And so there's a huge efficiency benefit from asserting, say, once every 10,000 blocks every hour or so. This whole protocol is managed and refereed by L1 contracts running on Ethereum. This is the basic picture. Okay, also important in the current protocol is staking. Any validator is allowed to stake on any pending assertion, and they're implicitly staking not only on that assertion, but on its predecessor and the entire chain of predecessors all the way back to Genesis. And so you don't need to stake on each assertion that you claim is true. You just stake on sort of the leaf or the end of the chain that you believe is correct, and you're implicitly staking on everything earlier. Every pending leaf will have at least one stake on it, because anything that is not either staked on or the predecessor or indirect predecessor of a staked on thing will be pruned off. And if your stake is challenged and you lose and your branch is determined to be wrong, then your stake is slashed. And that's what creates the incentive not to stake dishonestly. All right, so in the normal case, again, in the current Arbitrum protocol, before we introduce BoLD, this is the common case that you see normally. Over here on the left, you have some green. Let's see if my laser works. Yes. Over here on the left, you have a chain of confirmed assertions. And then hanging off of that, you have a long chain of pending assertions. And in this particular scenario, they have all been posted by Alice, and Alice is staked on the one at the end. And also, therefore, of course, implicitly on this whole yellow history. This is the normal case. And in the protocol, after a challenge period has passed, if there is no fork here, then this first yellow assertion will be confirmed. It will turn green. And so the way that we make progress is that these yellow ones will turn green in the normal case one by one. Meanwhile, Alice will be appending new assertions onto the end as the chain continues to make progress. That's the normal case. But of course, something like this can happen. Here we have a scenario where we have some chain of yellow assertions, and then we have Alice and Bob who are making different claims about how the history goes after this branch point, and each one is staked on the leaf of their particular branch. Now, when this happens, when there's a fork, now we have a challenge. The protocol will open up a challenge, and the job of the challenge is to identify that either Alice or Bob is lying. Now, if it identifies someone as a liar, maybe they lied by staking on a false branch, or maybe they lied during the challenge protocol itself, but regardless, they lied at some point, and so we will slash them, we'll kick them out of this, we'll take their stake away. And in this case, let's say Bob is identified as the liar through the challenge protocol. Bob is removed here. Now there's no one staked on this branch, and so this branch is pruned off by the protocol, and now we're back in the happy state where there's only one history. Now, if you are a participant in the protocol, and let's say you agree with Bob, you might not trust Bob. It might be, you might worry that Bob, even though Bob staked on the right thing, that he might be malicious and he might choose to lie and deliberately lose the challenge against Alice. And so if you agree with Bob, but you don't trust Bob, you'd better stake down here too. In fact, anyone can stake on any one of these assertions that are yellow. Then you might be called into a challenge to defend the particular branch that you're staked on. Challenges are 1v1. So here we said Alice and Bob are fighting each other. Maybe Charlie is staked up here and Diana and Ed are staked down here. And so then maybe Alice is in a challenge against Bob and Charlie's in a challenge against Diana and Ed just went to the beach for a while. Eventually, each of these one-on-one challenges will kick people out, and then roughly tournament style will reduce the number of parties who are still there until eventually there's only one branch with anyone left standing. And then the challenges are over. That's the current, how the current protocol works. So note, everyone might need to stake to defend their own knowledge of the truth, because you can't trust someone just because they happen to be staked honestly in the current protocol. Okay, so what properties does this current protocol give you? First, it gives you trustless safety. If there is at least one validator behaving honestly, that includes you potentially, then no bad assertion can be confirmed. Second, trustless liveness. If there's at least one honest validator, then some assertion will be confirmed. And because of trustless safety, that will be a good assertion. Third, if all the validators follow incentives, then the protocol will execute efficiently. There will never be a dispute, and you'll get minimum time to confirmation. But a malicious validator or a collusion of malicious validators or a single malicious validator using civils can cause delays. And although it's not obvious from the description I've given you, in fact, the worst case delay attack against this allows an adversary attacker to delay confirmation by end challenge periods if it's willing to sacrifice end stakes. And so that's a significant griefing attack. And even if the stake is very large, this doesn't make us happy. And this, in fact, is why on currently deployed Arbitrum chains, the validator role is permissioned. But we like to get rid of that. All right. But before I go on and talk about the BoLD protocol, which does get rid of that problem, let me talk a little bit about Ethereum censorship and the challenge period. Now, any L2 protocol is going to rely on the ability to post transactions on Ethereum. And Ethereum is subject to censorship attacks. And because we have an extreme amount of value at stake in this protocol, arguably for the Arbitrum 1 chain, more than $10 billion of value, we can't be casual in thinking about this possibility of censorship on Ethereum. We have to assume a really, really bad worst case. The current social consensus about Ethereum censorship, and this again is a very complex topic, be happy to talk about it offline with anyone, is that no censorship longer than 7 days on Ethereum will occur, or if it does, there will be a social response, a sort of out-of-protocol social response that will address it. And so we assume in the design of the current protocol that in the worst case, there might be up to 7 days of censorship. And in particular, let me talk for a moment about how we build that in a slightly more formal way into our threat model. So the threat model works like this with respect to censorship. Normally, an Ethereum transaction that gets submitted at time t will be included in the Ethereum chain by time t plus delta, where delta is, think of it as 5 minutes. But the adversary has the ability to enable or disable a notional censorship mode. And they can turn censorship mode on and off as much as they want. The only constraint is they can only have it turned on for a total of up to some maximum time C, which you can think of as 7 days. During censorship mode, the adversary has the power to freeze any transaction it likes. So that transaction or those frozen transactions don't make progress in counting up their time of delta in order to actually get included in the chain. So as long as the adversary keeps you in censorship mode, they can block your transactions inclusion for as long as they want, while allowing their own transaction and their friends' transactions to get on really fast. In fact, in censorship mode, the adversary's transactions can have no delay at all if the adversary wants. The adversary completely controls block building during censorship mode. Okay, so that's how we build this into the threat model. Okay, now, let me talk about the BoLD protocol, which is the new challenge protocol for Arbitrum. And it's different in a bunch of important ways. Some of these ways here, some of these differences, it may not be obvious how to achieve them. I'm going to give you some intuition, but the design is a bit more complex than I can go through in a single talk. But let me talk a little bit about the difference between the old protocol and this new BoLD protocol. In the old protocol, when there's a challenge, a disagreement, the challenge is a one-on-one contest between two stakers. And the outcome of the challenge is to identify one of those stakers as a liar. So we're going to remove that staker. And it naturally takes a tournament or multi-round process of these challenges if there are more than two people who are staked. In the BoLD protocol, a challenge is all versus all, so that if you have a 9-way branch in this tree of assertions, there's a single challenge to resolve that 9-way disagreement. And the contestants in that challenge are not individual stakers, but they're the branches. And what the challenge does is it chooses one branch as the winner. So that's much more efficient. You don't have a multi-round tournament. Everything, if there's a branch in this tree, it gets resolved within a single challenge protocol, which has a single upper bound on its running time. In the old protocol, each party has to stake and fight separately because people who are acting like your teammates so far might turn out to be malicious and stab you in the back later. So you have to stake and you have to fight challenges individually. In the BoLD protocol, you just need one party to stake honestly. As long as one party stakes honestly, even if they turn out to be malicious, they can't stab you in the back. All the honest parties can also fight as a single decentralized team. And again, if some members of that team are acting honest so far, you don't have to worry that they'll stab you in the back or take a bad action on behalf of the team, because the protocol is designed so it's not possible for them to do that. This, again, leads the result to be much more efficient. You need only one honest stake, and you need only one party to take each honest move in the protocol. You'll see what I mean a little bit later. And the result of this is that whereas before we had the possibility the adversary can cause n weeks of delay by sacrificing n stakes, in the BoLD protocol, the adversary can cause 1 week of delay no matter how many stakes they're willing to sacrifice. And then also in the old protocol, the honest party's total cost in one of these challenge tournaments, it would be proportional to the number of honest parties who participate, which might be large because remember, every honest party, to be safe, will probably want to participate. Whereas in the new protocol, the honest party's total cost is proportional to the number of stakes they take from the bad guys. And that's not only likely to be a much lower number, but also it conveniently is the case that the amount of cost the honest parties take on that you'd like to reimburse is exactly the same as the number of stakes that you're going to take. So you can use the bad guys' stakes to pay back the honest party for their labor in the protocol. Although I have to admit, we have not implemented that piece yet. Okay, let me tell you a story about how the BoLD protocol works, of an execution of the protocol to give you an idea of how it works. So here we have over at the left an assertion, a claim that says at a height of 0, and that 0 is with reference to the point at which the branch occurred. At a height of 0 after the branch, this represents a claim about that state. And this is known to be correct because we know at the branch point, at least for purposes of this challenge, we're trying to figure out which of these 3 claims on the right would be the correct successor of this one, or slightly more formally, if this one turns out to be correct, the winner will also be correct. If this one is wrong, the protocol doesn't care who wins, which one of these wins. Okay. So up here we have another claim. This is a claim at height 2048, meaning 2048 blocks later. And there's a particular Merkle value that's here. And this Merkle value is a commitment via Merkle tree to the entire history of blocks from height 0 up to height 2048. So it's a commitment to the entire history. And here we have 3 different claims here, each with a different Merkle value, which are committing to different histories of the chain from height 0 up to height 2048. So this is the starting point of a challenge. Now, one of the first things that someone might do in a challenge, and in our particular story, anyone is going to bisect this top edge. What that means is they're going to insert into the middle of it a specific claim at halfway between height 0 and 2048 at 1024, and they assert a certain Merkle hash of the history up to 1024. Now, in doing this, they have to prove that their Merkle claim here is consistent with the Merkle claim at the end. And that, roughly speaking, means that this is a commitment to a sequence of the right length, which is a prefix of the history that's being committed to here. It's a little bit more complicated than that. And if you're a cryptographer, you're going to see what else I would have to prove. Trust me, we have proven that. Okay, so, but the important thing to notice is 2 things about this. First of all, there's a unique value that can be the Merkle claim here. Because the hash function that we use for the Merkle tree is collision resistant, there's a unique value here. And that means that even if the person making this move is malicious, they have to make the move that this person had in mind, assuming this person is not evil and didn't have anything in mind. And in that case, again, the protocol doesn't care. So there's no option in terms of what Merkle you put here in this commitment, and there's no option about the height. You have to be in the middle, right? And so everyone who is acting to defend this branch can only make a single move, which is consistent with the claim that was made at this leaf. Okay, thanks. So now, at this point in the protocol, these red edges are called presumptive edges. This is an important concept in the protocol, a presumptive edge. And so what it means is, to be a presumptive, an edge needs to be shorter. Either it needs to have no rivals, or it needs to be shorter than its rivals. And presumptive means that if nothing else happens, these edges are going to be the winners. And there's a timer running on each presumptive edge, which keeps track of for how long it's been presumptive. If it's been presumptive for long enough, it will automatically win by default. And this gives the other branches, the advocates of the other branches, incentive to do something. What do? Well, the middle branch, that might bisect. Oh, and look, the middle branch, of course, was also forced that particular Merkle value in the middle. It happened to be the same as this one. So rather than duplicating that vertex in this graph, we in fact we do this. And so now you can see these 2 branches agree up to here. This edge is still presumptive. This one is not anymore because it's no longer shorter than its rival. Next thing, the bottom one might be bisected. Now this one is no longer, it happens to have a different Merkle at height 1024. Now this is no longer presumptive, but this one is, it doesn't have a rival. Now next, let's say this edge gets bisected, and you have this, again, you have presumptive edges here, and you can see kind of intuitively what's going on here. You want to make your own edges presumptive, or at least stop your opponent's edges from being presumptive. That's how you win. But this process is going to force you to bisect where there's a disagreement. And let's say this one gets bisected again, you might end up resulting here. And what you've seen is we've taken a big disagreement, and now we've taken a 3-way disagreement. We've broken it down into 2 two-way disagreements, and each of them is smaller than we started out with. This process will continue narrowing down the disagreements, etc., unless someone just defaults, stops defending their edge, and then their rivals will win by presumptive timeout. Okay, so you keep bisecting. Eventually, you might get down to a situation like this, which we call a one-step fork. And now you can do a one-step proof over a single block or a single step to prove that one of these branches is correct. That gets marked as correct. It becomes presumptive. And this one can never be presumptive anymore because it can never be proven correct, because this is the correct one. It's proven correct on the merits, which you can do for a single step. Okay. Now, the protocol uses timers, and there's 2 notions of timer. There's the edge timer, which is on a single edge. It measures for how long that edge has been presumptive. And then there's a notion of inherited timers, which basically says that if an edge has accumulated some presumptive time and you bisect it, its children inherit that presumptive time. And so there's a notion of an inherited timer, which means roughly what you'd expect it to. And the protocol says you can confirm an edge if one of three things is true. If that edge is one step proven, or if its inherited timer is at least the challenge period of 1 week, or if both of its bisection children have been confirmed. If two short edges are confirmed, then the thing that that was bisected to make them can also be confirmed, and recursively all the way up to the overall initial claim. So there's an honest strategy here, which is pretty simple, that honest parties should follow. Make an honest assertion at top level if nobody has, and then after that, defend every honest edge. And defending an edge means if you can confirm it, do that. If you can one-step prove it, do that. And otherwise, if it's not presumptive, bisect it. When you bisect, you'll create two new honest edges, which you'll also want to defend concurrently. And again, the honest parties can team up. You don't need to defend every edge yourself. You can just watch. And if someone else is making the unique honest moves, deterministic honest moves to defend that, then you're happy. And we can prove two things now. The safety theorem, if any one party follows the honest strategy, then it's safe. No dishonest top-level edge will be confirmed. And then also the completion theorem. If any one party follows the honest strategy, the protocol will complete safely within time of 2C, that is 2 challenge periods, plus a lower order term. Now, because the completion time is C, even if there's not a dispute, this means that you add another C plus some low order stuff. So basically, think of it as 7.5 or 8 days of extra delay. And that's true no matter how many stakes the adversary is sacrificing. Once the dispute's over, the protocol will catch up and you won't have lost any time. All right, let me talk about the status of this now and the path forward. The code, working code for this, a paper describing it, and a security audit of that code and the protocol have been published on the Offchain Labs website in our GitHub. There's a testnet coming soon. And after the testnet, this will be available for orbit chains. That is, people who want to launch their own Arbitrum chains will be able to adopt this. And it will be available for the Arbitrum DAO to consider deploying on the flagship Arbitrum 1 and Nova chains. So this is out there. If you have questions, I'd be happy to talk afterward. More technical details in our paper. I think I'm just about at time, but let me also thank my teammates who all played important roles in making this happen, including Raul and Terrence, who are here today. So, so you're also welcome to ask them questions about it. And that's all. Thank you very much. And I hope we have time for questions.